The Giotto and Vega missions gave planetary scientists their first view of Halley's surface and structure. Like all comets, as Halley nears the Sun, its volatile compounds, those with low boiling points, such as water, carbon monoxide, carbon dioxide and other ices, begin to sublimate from the surface of its nucleus. This causes the comet to develop a coma, or atmosphere, up to 100,000 kilometers, 62,000 miles, across. Evaporation of this dirty ice releases dust particles, which travel with the gas away from the nucleus. Gas molecules in the coma absorb solar light and then re-radiate it at different wavelengths, a phenomenon known as fluorescence, whereas dust particles scatter the solar light. Both processes are responsible for making the coma visible, as a fraction of the gas molecules in the coma are ionized by the solar ultraviolet radiation. Pressure from the solar wind, a stream of charged particles emitted by the Sun, pulls the coma's ions out into a long tail, which may extend more than 100 million kilometers into space. Changes in the flow of the solar wind can cause disconnection events, in which the tail completely breaks off from the nucleus. Despite the vast size of its coma, Halley's nucleus is relatively small, barely 15 kilometers, 9.3 miles, long, 8 kilometers, 5.0 miles, wide and perhaps 8 kilometers, 5.0 miles, thick. Its shape vaguely resembles that of a peanut shell. Its mass is relatively low, roughly 2 times 10^14 kilogram, and its average density is about 0.6 grams per cubic centimeter, 0.35 ounces, cu in, indicating that it is made of a large number of small pieces, held together very loosely, forming a structure known as a rubble pile. Ground-based observations of coma brightness suggested that Halley's rotation period was about 7.4 days. Images taken by the various spacecraft, along with observations of the jets and shell, suggested a period of 52 hours. Given the irregular shape of the nucleus, Halley's rotation is likely to be complex. Although only 25% of Halley's surface was imaged in detail during the Flyby missions, the images revealed an extremely varied topography, with hills, mountains, ridges, depressions, and at least one crater. Halley is the most active of all the periodic comets, with others, such as Comet Encke and Comet Holmes, being 1 or 2 orders of magnitude less active. Its day side, the side facing the Sun, is far more active than the night side. Spacecraft observations showed that the gases ejected from the nucleus were 80% water vapor, 17% carbon monoxide and 3 to 4% carbon dioxide, with traces of hydrocarbons, although more recent sources give a value of 10% for carbon monoxide, and also include traces of methane and ammonia. The dust particles were found to be primarily a mixture of carbon, hydrogen, oxygen, nitrogen, CHON, compounds common in the outer solar system, and silicates, such as are found in terrestrial rocks. The dust particles decreased in size down to the limits of detection, approximately equals 0.001 micro-m. The ratio of deuterium to hydrogen in the water released by Halley was initially thought to be similar to that found in Earth's ocean water, suggesting that Halley-type comets may have delivered water to Earth in the distant past. Subsequent observations showed Halley's deuterium ratio to be far higher than that found in Earth's oceans, making such comets unlikely sources for Earth's water. Giotto provided the first evidence in support of Fred Whipple, S. Dirty snowball. Hypothesis 4. Comet construction. Whipple postulated that comets are icy objects warmed by the Sun as they approach the inner solar system, causing ices on their surfaces to sublimate, change directly from a solid to a gas, and jets of volatile material to burst outward, creating the coma. Giotto showed that this model was broadly correct, though with modifications. Halley's albedo, for instance, is about 4%, meaning that it reflects only 4% of the sunlight hitting it, about what one would expect for coal. Thus, despite appearing brilliant white to observers on Earth, Halley's comet is in fact pitch black. The surface temperature of evaporating, dirty ice ranges from 170 K -103 degrees Celsius at higher albedo to 220 K -53 degrees Celsius at low albedo. Vega 1 found Halley's surface temperature to be in the range 300 to 400 K 27 to 127 degrees Celsius. This suggested that only 10% of Halley's surface was active, and that large portions of it were coated in a layer of dark dust that retained heat. Together, these observations suggested that Halley was in fact predominantly composed of non-volatile materials, and thus more closely resembled a snowy dirtball than a dirty snowball.